Hello students, I am Satyaprakash. Welcome to Cars Physics. This is my lecture 2 on electric potential. In previous lecture, we have discussed on qualitative idea on electric potential. Okay. Before that, under electrostatic, we have already discussed the complete subject on electric charge and electric field. Okay. Then I like to say you all who have not gone through the first subject, electric charge and electric field, as well as lecture 1 on electric potential. Go through all these lecture 1 on electric potential and on the whole subject based on electric charge and electric field, then enter to lecture 2. And I hope, I am sure, I can assure you, your fundamental concept will must be clarified. Okay? Okay. Now come to the point. In lecture 1, we have discussed qualitative idea on electric potential. As we have discussed, to express electric field, we require number 1, electric field vector, or number 2, electric potential difference. Okay? Electric field can be expressed by the help of electric field intensity or electric field vector and electric potential difference. We have discussed about qualitative idea on electric potential as we have discussed. Electric potential is electrical condition of a charged body. Okay? As we have discussed, if heat is given to a body, then we do say temperature rises. Okay? If fluid is blown or given to a container, we do say pressure is rising or pressure increases. Heat is cause and temperature is effect. Fluid is cause, pressure is effect. Temperature determines direction of flow of heat. Pressure determines direction of flow of fluid. Similarly, potential determines direction of flow of charge. Temperature is thermal condition and potential is electrical condition of a charged body. Also, we have discussed potential of a body depends upon nature of charge. Okay? Potential is positive due to positive charge. Potential is negative due to negative charge. And a neutral body, uncharged body, has zero potential. Okay? We have discussed on all these concepts, and again we have got a simple quantitative idea on electric potential difference, thereafter on electric potential. Okay? In this lecture, we will discuss on quantitative idea on electric potential and electric potential difference. Okay? We will have quantitative idea on electric potential and electric potential difference. Okay? This is a derivation-based class, derivation-based lecture. So directly speaking, we are going to find derivation of electric potential. Okay? As we have discussed, electric potential can be calculated for a single charged body, single charge. Number 2, due to a system of charges. And finally, due to an electric dipole. electric dipole. Electric potential can be calculated, or we can get quantitative idea or derivation in these three cases. For a single charge, for system of charges, and for an electric dipole. We'll discuss all these gradually. In this lecture, we'll discuss electric potential for a single charge. Okay? Electric potential due to the single charge or electric potential due to a point charge. Okay? Electric potential due to a single charge or due to a point charge. Okay? In this class, we get derivation of electric potential due to a point charge, means quantitative idea on electric potential due to a point charge. Okay? Suppose this is a point charge. Let this point charge is Q. This charge Q plus Q is field creating charge, or we may say it source charge. A point charge Q is field creating charge. If a point charge is placed in space, let's assume a point charge is placed in space, then it produces an electric field all around it. And as we know, range of electric field is up to infinity. Range of electrostatic force is up to infinity. Okay? Electric field is extended up to infinity. Electric field is extended up to infinity. Okay? Then electric force also can work, or a charge can exert electrostatic force of attraction or repulsion on other charge up to infinity. Okay? Range of electrostatic force is infinity. Okay. This charge is field creating charge. There is an electric field all around it. Okay? We have to find electric potential due to this point charge at any point P at a distance r from the point charge. We have to find electric potential at point P due to this point charge. Of course, electric field at point P due to this point charge is given as kq divided by r square, as we have discussed it in chapter 1 in electric charge and electric field. Similarly, we have to find electric potential at point P due to this point charge. Okay? So what we have discussed? Electric potential, we have discussed in lecture 1, electric potential due to a point charge at any point, let P. Electric potential at any point P is amount of work done in moving a test charge, and as we know, conventional test charge is unit positive charge. In moving a test charge means unit positive charge from infinity to any point, to that point, but external agent. It is already discussed in lecture 1. Electric potential at any point, 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 elec can be calculated or is defined as quantitative form. In quantitative form, electric potential at any point in the electric field, electric potential at any point in the electric field is produced by this point charge. Electric potential at any point P is defined as the amount of work done in moving a test charge or unit positive charge from infinity to that point by external agent, means by applying external force. See, if we place a point charge here, let point charge is plus Q0, unit positive charge. Okay, then this point charge will be repelled by this unit positive charge, and obviously this unit positive charge will move away due to repelling force produced by this field creating charge. It will be repelled towards infinity. Okay, then no force is required to move the charge towards infinity. If the charge were negative, automatically this charge will be attracted towards it. But we have to move the charge by external force. Okay, then I think you have written this definition. This is definition, quantitative definition. Quantitative definition of electric potential due to a point charge. This is quantitative definition. I think you have already taken it, or you may take screenshot. Okay. In simpler way, we can write electric potential. Electric potential symbol is V at point P is defined as amount of work done by external agent. Amount of work done by external agent in moving the charge from infinity to point P. Okay. Amount of work done in moving a test charge from infinity to point P by the help of external agent, and as you know, electric potential at any point is work done per test charge or work done per unit positive charge. Okay, this is simpler way to explain electric potential. Amount of work done to bring an unit positive charge from infinity to a given point P by the help of external agency. Okay, then what we will do? We will bring an unit positive charge or test charge from infinity to the required point P by the help of external agent. Means we have to bring the charge, we have to move the charge from infinity to this point. Okay, I am going to infinity, but okay, I have reached that infinity. Now I will take the charge, test charge from infinity to the required point P. Right? This is infinity. This is infinity. Okay? This is infinity. I have to bring the charge from infinity to this point. Okay? I have to bring the charge from infinity to this point P. But we don't know. We don't have any information. We don't have any idea what is the actual force, accurate force on test charge if it is placed at infinity. We have no information. What is the exact force acting on this unit charge due to the field creating charge at infinity? Since force is extended up to infinity, what is the exact force? We don't know the exact distance. So, if this is infinity and you displace this charge from infinity to this point, then this is infinity. Let displaced distance is dx, or if you move away from infinity, this is infinity minus dx, this is infinity plus dx. So infinity plus dx is infinity, infinity minus dx is also infinity, so total distance is infinity. We don't have idea on electrostatic force on a test charge at infinity. Okay, so then another condition, to move the charge, we have to move the charge slowly. As we have discussed in lecture 1, we have to move the charge, means by the application of external force, we will move the charge from infinity to this point slowly, means with uniform speed or with constant kinetic energy. So while moving the charge, speed must remain constant, or kinetic energy must remain constant. Without changing speed or without changing kinetic energy, we have to move the charge from infinity to the required point P, which is at a distance r from the point charge. Okay, we have no idea on electrostatic force at infinity. Let's consider any point A. Let's consider any point A at a distance x from the field creating charge. Let's consider any point A at a known distance x, from the field creating charge. Let's place here the test charge or unit positive charge. See, this test charge will experience a force due to the field creating charge. This is positive, test charge is taken as positive, so it will experience a force, means this force is electrostatic force, which is towards infinity. But we have to move the charge slowly. We have to move the charge slowly from infinity to point P. To move the charge slowly, resultant force, means to move the charge with constant speed or uniform speed, resultant force must be zero. Means we have to apply an external force. We have to apply an external agency whose the magnitude of external force or external agency should be exactly equal to electrostatic force. So the applied force or external force must be applied in opposite direction so as to move the charge from infinity to point P. Okay. See, against the electrostatic force, we have to displace the charge from infinity to point P. Let's consider a small displacement from A to B, dr. A small displacement, let dx. Small displacement is dx. Point A is at a distance x from the source charge. Let the charge is displaced from position A to position B through a small displacement dx under the action of external force. Okay, but this external force is exactly equals to electrostatic force in magnitude but opposite in direction. So external force is equal to electrostatic force but in opposite direction. Magnitude same but direction is opposite. Okay. See, if we leave the charge, if we place the unit charge or test charge at this point, then obviously under the effect of electrostatic force, it will be displaced in outward direction, means towards infinity. But we have to move the charge towards the field creating charge means towards point P. Okay. So here work will be negative. Work will be negative. Okay. Due to electrostatic force, work will be negative. Electrostatic force is towards infinity. Displacement is towards point P. Okay. Then displacing the charge. This is our basic form. Displacing the charge, displacing the test charge from A to B. Displacing the test charge from A to B against electrostatic force. Against electrostatic force. Here, as we have discussed, magnitude of external agency is equal to magnitude of electrostatic force. Okay. So, displacing the charge from A to B against electrostatic force. Against the electrostatic force, work is dW since the displacement is very small. So, electrostatic force dot displacement dx. Electrostatic force is towards infinity. Dx is towards the source charge. So here, angle between them. See, this is the direction of electrostatic force, and this is the direction of displacement from A to B. From A to B. So angle between electrostatic force and displacement is 180 degrees. They are oppositely directed. So dW is equal to my electrostatic force into dx into cos 180. So dW is equal to cos 180 is minus 1 electrostatic force into displacement. Okay. But we have to employ external agency. We have to employ external agency. External force is equal in magnitude with electrostatic force. We have to employ external force. So dW is equal to minus magnitude of electrostatic force is magnitude of external force into dx. Okay. Then external force. I am writing here external force or electrostatic force. Both are in same magnitude. External force or electrostatic force at a distance x, k, q, q0 by x square. Field creating charge q, test charge q0, distance between them is x. So dW is equal to minus k, q, q0 by x square into dx. Okay. Then to get the whole work, we have to bring the charge by the application of external agency from infinity to point P. So to get total work done at infinity 0, because if distance tends to infinity, then force is negligible, work is negligible, 0 to W dW. Integration of minus k q q0 by x square into dx, we have to bring the charge from infinity. This is field creating charge q. We have to bring the charge from infinity to a given point P. So distance varies from infinity to r. Point P as it at a distance r from the field creating charge. So distance varies from infinity to r. Okay. So integration of dW is W minus k q q0 integration of 1 by x square into dx. Limit varies from infinity to r. Okay. Then work is equal to minus k q q0 integration of 1 by x square. This is infinity is minus 1 by x. Limit varies from infinity to r. Okay. Then work is equal to minus k q, sorry, this is q naught, k q q naught into minus 1 by r minus 1 by infinity. Minus minus multiplied, we get positive k q q naught. 1 by infinity is 0, then remaining is 1 by r divided by r. This is formula for work done. Okay? But potential at point P is work done by external agent to bring the test charge from infinity to point P. Okay? Then, final expression, I will erase this side. Can I erase it? Okay. Then, work. We got work. Then potential at point P is work done by external agent to bring the test charge from infinity to point P. Work is k q naught by r divided by test charge q naught get cancelled. Then potential is k q by r. This is potential at a point P due to a point charge. Okay. Of course, as we know, work done is independent of path. I am showing this. I am erasing this. Okay. If this is the field creating charge and this is infinity, we have to bring the test charge from infinity to point Q along this path or along this path or along this path, so whatever be the path. Work is same because the electrostatic force is conservative force, electric field is conservative field as that of gravitational force and gravitational field. Okay. Then this is positive, this is also positive. Then work done by external agent is equal to negative of work done by electrostatic force. Okay. Electrostatic force tends to repel the charge towards infinity. External force brings in opposite direction. Since the forces are in opposite direction, work will be negative. Okay. Negative means depending upon direction of force. Okay. Work done, simple thing, work done in a complete path is 0. See, this is point A, this is point B. Okay. If you take a charge along this path, this is W1, work done is W1, and again you bring this charge from B to A, work is W2, then W1 plus W2 is equal to 0, or W1 is equal to minus W2. So, work done by external agent is equal to minus work done by electrostatic force. The same thing, the condition is here because magnitude of external force is equal to magnitude of electrostatic force. This is the concept. Okay. You go through the concept in physics. First, understand the basic concept, think it, perceive it, feel it. Then physics will be made easier for you. Nothing is difficult in physics to approach the theoretical questions or numericals will be made easier if you have clarity in your understanding. This is potential due to a point charge at any point P at a distance r from the point charge. Okay. Then some points on electric potential. We got electric potential. The condition is to get electric potential at a point, we have to bring the charge from infinity to the required position by the application of external force, and the charge should be moved slowly, means with constant speed, with uniform speed or without changing kinetic energy. Okay. In general, see, potential at point P is kq by r is the distance. In general, we may write potential at any point is K Q by R. At any point P or A or B, whatever we may take, okay. In case RSR, potential is equal to K 1 by 4 pi epsilon into Q by R. In vacuum, potential is equal to potential in vacuum or air in vacuum. Potential is equal to 1 by 4 pi epsilon naught into Q by R. In a medium, potential in medium is equal to, in place of 4 pi epsilon, we can write epsilon naught into Q by R. Okay. See it. In medium, potential in medium is equal to 1 by epsilon R times 1 by 4 pi epsilon naught into Q by R. So we may write potential in medium due to a point charge at same distance R is 1 by epsilon R times potential in vacuum. Potential in vacuum. Thus, for a point charge at a given distance R, potential in medium decreases by 1 by epsilon R times as that of potential in vacuum or air. So, simply you may write potential in medium divided by potential in vacuum is equal to 1 by epsilon R, or potential in vacuum is equal to epsilon R times potential in medium. Okay. Thus, potential decreases in a given dielectric medium or insulating medium as compared to that of in vacuum. Okay. Next point. I will take in all these. Take screenshot. Okay. Potential is KQIR for a point charge. For a point charge, potential is KQIR. So potential inversely proportional to distance from point charge. So the required variation of potential with distance, not so steeper. With increase in distance, potential goes on decreasing. Okay. So this is about electric potential due to a point charge, and then we'll move to potential difference. Okay. Potential difference. See. The diagram, let it be same. Potential difference. Potential difference between any 2 points. I am erasing the diagram so that it will be very easier. Also, this is very easier way to get it directly also. I am showing you the easier way. Let this is a point charge producing field all around it, and this is L2. This is any point B, this is any point A. Point A is at a distance RA from the point charge. Point B at a distance RB from the point charge. Then potential difference between any 2 points in the electric field is amount of work done by external agency or agent in moving a test charge from initial point to final point, or one point to another point. But it should be remembered, work done by external agent and motion of the charge should be slowly. All these facts are there. Okay. Then potential difference is the amount of work done by external agent in moving a test charge from initial. See, this is point charge, this is infinity, this is initial point. We have to place on unit positive charge at point B, then we have to move the point charge, the test charge from B to A. This is initial position and this is final position. Okay, we can derive it, also we can get it easily. See, potential at point A. As we know, potential at any point is K Q by R. Potential at point A is K Q by R. Similarly, potential at B is K Q by RB. Distance of B from point charge is RB. Then potential difference between A and B, VA minus VB. This is final position, this is initial position. Final potential is VA, initial potential is VB. Difference in potential is VA minus VB. So this is equals to KQ by R minus KQ by RB. So finally we may write KQ into 1 by R minus 1 by R. This is easier. We, in place of K, we may write 1 divided by 4 pi epsilon. Okay. Epsilon, in place of epsilon, we may take epsilon naught, epsilon r, or only epsilon naught if medium is vacuum. Okay. This is the definition. Can I erase it? Again, you can derive in similar way. Okay. Let's place this is infinity, an unit positive charge at any point P at a distance x from the field creating charge towards infinity. This is electrostatic force, and towards the source charge, this is external force. Under the effect of external force, the charge is displaced from P to Q through a small displacement dx. Again, small work, as we have taken electrostatic force, that displacement, angle between them is 180, electrostatic force and displacement are in opposite direction. This is electrostatic force into dx into cos 180. So dW is equal to electrostatic force against electrostatic force because external force is opposite in direction to electrostatic force into dx minus. So as we know, magnitude of electrostatic force is equal to magnitude of external force in magnitude. To move the charge slowly, resultant force should be 0. So we may write dW is equal to external force minus into dx. Since initially the charge is at point P at a distance x, in place of force, we may write K, Q, Q naught by x square into dx. To get total work, resulting work will be W minus k q naught. Bring it outside. Integration of 1 by x square into dx. We have to displace the charge from point B to point A. This is actual displacement between these 2 points, point B to point A. So variation of distance is from RB to R. So this is what? Minus k q naught. 1 by x square. Integration of 1 by x square is minus 1 by x. And variation of distance means limits RB to R. Okay. Then work is equal to minus k q naught minus into minus plus k q naught into 1 by R minus 1 by R. Then potential difference dV, we may take potential difference dV is equal to work done, net work. So you may take, this is W1 to W2. So this is W2 minus W1 or dW, or you may take it W. Okay. Work done per unit charge. So dV, by bringing a test charge, so dV is equal to k q naught into 1 by RA minus 1 by RB divided by q naught. So potential difference is kq into 1 by RA minus 1 by RB. See, this is derivation for potential difference if point B is at infinity, means if RB is infinity, then dV means VA minus VB is equal to KQ into 1 by RA minus 1 by infinity. So potential at infinity, we may write point B is at infinity. So finally we may write, this implies potential at infinity is 0, 1 by infinity is 0. So VA is equal to KQ by RA. So this is our previous result. Potential, we got potential at position A from the expression of potential difference. Okay. These are basic discussions, fundamental derivations. These are useful for your board level questions and for school level questions. Okay. This is the end of lecture 2. Only we have done some derivations for mainly we have focused on electric potential, derivation of electric potential due to a point charge. Okay. In next lecture, we'll discuss some conceptual discussions on electric potential. Okay. So far, thank you. Thank you, my dear students. Thank you for your sincere support. Thanks.